This is Austin Hoggett, here to give you another OpenStax Intermediate Algebra lecture. This time we're going to be talking about some factoring techniques. Taking a look here, you can see that there's sort of this branched general strategy for factoring polynomials. One of the first things that we typically will ask ourselves, given some expression that needs to be factored, is if we can identify a GCF. So that's sort of the starting point for each of these branches. The next thing that we need to consider is how many terms are left after sort of considering if there's a GCF. Mainly what we're going to concern ourselves with today is this middle branch, trinomials. And they kind of come in two different flavors. That's the x squared plus bx plus c format and the ax squared plus bx plus c format. And in both cases we use what's called the AC method. So that is our focus here, factoring trinomials in the format that you see here. Very specifically, we can generalize and say that this is really the same type of problem, but there's two versions of it. There's the quote easy version and the hard version. So how do we distinguish between the two? Well, we say that the easy version is if the coefficient on the square term is equal to 1, and the hard version is, well, when it's not. So what makes these easy versus hard is something that we'll talk about as we kind of explain the method itself. But the nomenclature, AC method, is derived directly from the standard format of this equation, this ax squared plus bx plus c form. So let's start with the easy version. If we're asked to factor a trinomial in the form x squared plus bx plus c, how can it be done? Let's start with an example where we know the solution already. For instance, here we have the product x squared plus 5x plus 6, and we know that the factors here are x plus 2 times x plus 3. And we could actually confirm that using the FOIL method, which is partly just repeated distribution. But let's generalize from this idea. If a trinomial factors to give me a product of binomials, we just need to figure out the specifics of what those constants should be. So on the right hand side here, you can see I've generalized and said, well, what if we just have some random integer value, m and n? If we do the product following the FOIL method, we should get here something like x squared plus n times x. Now n and m here again just represent some constants, and so it should be relatively trivial to sort of abstract this idea that those are just like 2x and 3x would be had we done the product on the other side, right? So by the FOIL method we should get something like x squared plus 3x plus 2x, and then 3 times 6 gives me the last constant at the end of that product. But just as usual, we get the same sort of pacing of terms here. By that FOIL method, we should expect then that these two terms, just like in the exact example here, add together. And so we can claim a couple of things that are important here for understanding how this method works. One of which is that if nx and mx are just constants, we should be able to add them together, and that should actually be the same as whatever our middle coefficient would be. And it stands to reason as well that the product m times n should actually end up being the same as whatever my constant at the end would be. And so those are the two questions that we'll pose here. What values add together to give me the middle coefficient, but also multiply together to give me the constant at the end? That's what makes up this AC method. So just to summarize, here, we'd say that if we can factor something of this form, x squared plus bx plus c, we're not always guaranteed that we'll be able to. If it does factor, though, it will always give me this format, x plus m and x plus n. But we have to be able to find two numbers that satisfy these two relationships, right? So we need to find values that multiply together to give me the constant at the end, but add together to give me that middle coefficient. So let's see how this is done in practice. So here's an example. We have x squared plus 11x plus 24. So again, my a value is equal to 1, making this the quote easy version of the AC method. And so our task is to identify the solution to those two questions we posed. So we need to find m times n equals to 24 and m plus n equals to 11. This is essentially a system of equations, and so we have two unknowns and two relationships. We should be able to solve for it. And so I would start in this case by identifying a list of factors that create the product 24. And from that list, then see which of those pairs of factors answers the second question. So what are all the different ways we can multiply two numbers to get 24? Well, we have 1 times 24. We could have 2 times 12, 3 times 8, and 4 times 6. Generally speaking, this list of factors is going to be pretty short, and so it makes for a quick sort of rounding up of potential answers here. Now, once I've generated this list, I'm no longer sort of, trying to conjure this answer up from memory, right? I can look at the list and see which of these also satisfies the second equation, which also adds together to give me 11. Well, it must be that positive 3 and positive 8 satisfy those two criteria. So that means, again, since we've been able to find the answer to those two questions, the product that we can put together here is x plus m and x plus n. Now, it doesn't matter which of these I call m and which of these I call n. So we'll just arbitrarily say m is 3 and n is 8. So our factors here give me x plus 3 and x plus 8. And there's my solution to this particular example. So that's the AC method. We pose the questions here. What are the factors of C that add up to B? Now, truthfully, this is not quite a complete version of the AC method. In fact, we should really be finding the factors of A times C that add up to B. And why did we not use this true format of the AC method? Well, if you'll notice, our A term was equal to 1. And so really, 1 times 24 just gives me 24. But in truth, this is the more technically correct version of the AC method. These are the questions that are necessary to pose. So let's look at one other thing in the context of these very specific trinomials, the easy version. And I want to point to sort of the critical aspects of the slide. When C, the constant at the end, is positive, that tells me something specific about the sign of my factors. It means that the m and n values are going to have the same sign. So if C is positive, the only way to create a pair of factors that gives me a positive result is if both of those factors are positive or both of those factors are negative. So how do we distinguish between which we have? Well, we have to then look at the middle coefficient. Recall the second sort of criteria that we have to meet. So if the middle coefficient is positive and my constant at the end is positive, you can see, for instance, here that our factors, m and n, must also be positive. They need to add to be positive as well as multiply to be positive. But if our sort of b term is negative, but our constant at the end is positive, that can change a little bit about which of the factors might need to get the negative sign, right? So that's something to be mindful of as you're kind of walking through this process. The questions we pose will be the same. It's just a matter of identifying the correct signs to attribute to those factors. So let's continue. Here we'll look at the, quote, hard version of the AC method, again, where A is not going to be equal to 1. And what we mentioned a moment ago is that for the AC method, what we really should pose is this question about what factors of A times C also add up to the B term, right? So the hard version of the AC method still involves the same pair of questions, right? But there is one additional step where we have to factor by grouping, and that's the critical aspect here. So in the AC method here, we'll start with the original questions that we may have posed. But that's not exactly where we end, because we can't go directly to a solution once we find those m and n values. In fact, what you'll see here is that what occurs is a breaking up of the trinomial, the original expression, into 4 terms. And really what this means is that we're going to take our middle term, bx, and split it up into 2 pieces. We're going to split that middle term using the m and n values that we find. And once I've created this 4-term expression, I can continue the problem through factoring by grouping. So let's practice an example of this as well. So in this case, again, we're using the AC method. It's helpful to point out exactly what your A, B, and C values are. So again, this is the AC method. We'll need to find the following: the factors of A times C, so that's 6 times 2, that also add to give me B, which is 7. So this is a relatively easy sort of question, again, because we can generate a list of factors for that constant, right? So 1 times 12, and truthfully this could be positive 1 times positive 12 or negative 1 times negative 12. Both give me the same positive 12, right? So the answer to what should the sign be, again, depends on the second equation. We are trying to add to be positive 7. So that's how we have to think about this approach. So continuing my list here of factors, we've also got 2 times 6, and we've got 3 times 4, and so again, that's sort of a short list. Of course, only one pair of these satisfies both of those equations, and it's 3 times 4. They will add together to give me 7, but they'll also multiply together to give me that positive 12 that I need. So generating a list of factors, searching through that list to see which adds together to give me my B term, then satisfies the 2 criteria. So we said that N and M here are found. What we do next is to take our original expression here and split it up into 2 parts. We're going to use 6x squared plus 3x plus 4x plus 2, like this, so that we can factor by grouping. And the key here to factoring by grouping is to look at the first 2 terms and the last 2 terms as pairs, asking ourselves what is their greatest common factor. Once we remove the GCF from each of those pairs, we should be left with some binomial, and the binomials here should match exactly. That's a critical aspect of this. So looking at, for instance, 6x squared plus 3x, I can tell that they have a common factor of 3x. If I were to remove that expression from each term, or another way to think about this is to divide each term by 3x, what would be left goes in the parentheses. So 6x squared divided by 3x would leave me with another, 2x in this case. And 3x divided by 3x, okay, that just gives me plus 1. So the product here, if we were to do distribution, should give me back the original. Now, when I go and look at the other pair, 4x plus 2, I should expect that the same binomial, 2x plus 1, should show up. And sure enough, the GCF between 4x plus 2 is just positive 2. So by division of 2 in each of those terms, I get something like 2x plus 1 as expected. Now, the final step is to recognize that binomial is our new GCF. By removing this common binomial from each term, I'm left then with my solution, the product of 2x plus 1 and the remaining factors 3x plus 2, like this. So this is what we could FOIL together to get back the original trinomial given to us in the first place. So the AC method follows a lot of the same sort of patterns that we saw a moment ago. There's just an additional step, though, of having to factor by grouping to accomplish the last few steps. So that's going to be it for this section. Next time we'll see some interesting aspects of factoring using special products that make use of a lot of the same type of patterns and developments from that.